Hi, hello everyone. Thanks for joining me today. So I'm very excited to be here with you and give you a tutorial lecture on human-centric AI. So this is a topic I'm pretty excited about. So I think this topic, human-centric AI, is more like an umbrella. A lot of topics can be put under this human-centric AI, such as explainability that we are talking about in this tutorial. Also, many other properties of AI models, such as generalization, robustness, also can be put under the human-centric AI. So this talk is more about introduction on this human-centric AI. So I will talk about some of my previous work on this direction and how they can integrate it with each other under this human-centric AI. So first, let me introduce myself. So I'm an assistant professor at the Chinese University of Hong Kong, and I will move to UCLA by the end of this year. So you can consider this talk is also about a summary of my previous research. So if you have the intention to join my lab, so maybe this talk is also a talk about the introduction about the research happening in my group. So nowadays, people are very excited about the success of AI. For example, in self-driving, the machines can understand the whole image and segment image into the semantic regions. Also, we have this mobile robots from Boston Dynamics that can do a lot of amazing things in the real world. We also have the AI AlphaGo or AlphaFold that can solve very challenging problems, such as playing the game of Go, as well as predicting the protein structures as we human experts do. On the other hand, we also have the challenge of the AI. So we see many car accidents made by the autopilot AI system. We also see the bias in the prediction given by the AI models against the underrepresented groups. We also see the rampant deepfake videos and images that cause privacy and the security issues. So given all those success and the challenge of AI, I think we humans should not thinking about what AI can do for us humans. We also need to think about what can we do about the AI models. So one of the most popular AI models nowadays are deep neural networks. So in many AI applications, deep learning or deep neural network have been working quite well. For example, in computer vision, we have the ResNet, Master RCN, RenderNet that achieve amazing performance in those recognition tasks. Also in natural language processing, so we have the transformer as well as this gigantic GPT-3 that outperform any previous NLP methods with large margin. Also in speech synthesis, we have the parallel web nets that can even help you order the foods from the restaurant. So people are very excited about the performance achieved by the deep neural networks. But before we are too excited about the neural networks that solve all the issues, let's come back to the history. So let's go back to 1950s. The founding father of Alan Turing once proposed this fundamental question, can machines think? So in this very influential paper, the computing machinery and intelligence, you can see he proposed this question in the first sentence of this papers. So under this question, can machines think? There is a key assumption. So the key assumption is that the machines should think like us humans. Machine shouldn't think like a sponge or fish. It should think like us humans. In other words, we humans should understand the thinking process and decision-making process of artificial intelligence. However, if we come back to the AI models we are so proud of, these neural networks, it's really difficult to figure out what's going on inside all those neural network, all those layers and parameters. If Alan Turing come to our days and we show him all those neural networks, probably he will be puzzled. Oh gosh, how can we better understand the models, whether those machines, those AI models work like humans? We don't know. So giving all those neural networks for different tasks, we can actually summarize its diagram into this very simple pipeline. So we have this neural network represented by the nodes and the connections. And when we train this model on massive number of data, so in testing time, then we can just give an input, then this neural network can give us the output. So input, output. So this kind of pipeline is very straightforward. So industry people really like this pipeline because they can simply download the pre-trained model and plug in their applications. Then this model can work on the fly without much tooling. However, for the people in academia like me, so I'm really confused by this pipeline. You know, sometimes it's really difficult to figure out what's going on inside the model, especially when this model gives us some crazy outputs. How can we analyze the decision making and analyze the figure of this AI models? So there is this fundamental question behind this AI model. Can deep AI models think like human, right? So given this pipeline, so behind this general question, can deep AI models think like humans? We also can ask many specific questions. For example, giving this output, so we can ask about why this output. So it's relevant to the explainabilities of the deep AI models. Can this AI model provide some evidence to justify its output? Also giving this knowledge representations from massive number of data, then we can ask about what's nerd insights. So it's about the interpretabilities of the AI models. Because what we want is not just the outputs prediction, we also want the whole decision-making process is interpretable and understandable to our human beings. That's why we have this tutorial, right? Explainable AI. It's also a very hot topic nowadays in artificial intelligence. Also, giving this input, we can ask about, can this AI models handle all the cases? So it's relevant to the generalization ability of the deep AI models. Because what we want is not only a very accurate prediction on the testing set, we also want this AI model can handle all the wide cases in the real world. So we want this AI model can be generalizable outside of the training distribution. So all those properties are properties that beyond the performance of the models, but very crucial to our human beings. So eventually we want to move towards this human-centric AI. So here, my approach to human-centric AI is to understand and improve the human-centric properties such as interpretability, steerability, generalizability, fairness of the AI model beyond their original performance. We also want to build this reliable interactions between humans and AI. So through this talk, I will give you 3 case studies to show you how we approach this human-centric AI. So these 3 case studies across different applications of AI. So first one is building explainable AI for classification. The second is building more steerable AI for generation. And the third one is more recent work that I'm pretty excited about. How can we move towards more generalizable AI for autonomy? So let's get into the first work. How can we build explainable AI for image classification? So, you know, image classification is a very common applications of deep neural network. You know, we train this model on massive number of images. Then we can just input the image, then the model will give us a prediction. So here I have a deep neural network. So it's a very standard RedNet trained on a data set called Places. I collected with my colleagues, former colleagues at MIT. So this Places database is a scene recognition database, which contains more than 10 million images. So we train a neural network on Places. Then when we input the scene image, so this model will give us outputs about the scene category. So for this particular input, you can see this model predicts 72% indoor booths. So here I upload another photo of mine. So this model gave me the prediction, 62% pitch, which is also a correct prediction. So here's another photo of my friend. So for this particular input image, this model gave me a very bizarre output prediction. So you think this image is a martial art gym with such high confidence, 95% confidence. But I'm pretty sure my friend is not like Bruce Lee or Shang-Chi, so he doesn't know any martial arts. So you may have a guess why this model give me this bizarre prediction. You may think maybe it's a slippery floor, or maybe it's a pose of this person, or maybe it's empty space, right? So to better explain the prediction given by the model, so along with my former advisor, Antonio Torraba and Odo Oliva, so we developed this method called class activation mapping, shortly as CAM, to analyze the decision-making of models. So basically, to utilize the internal activation of the neural network and their relation to the final prediction, so we can generate a heat map to highlight the most important region relevant to the output. So for this particular image, you can see this neural network actually identify the bare feet as the most evident regions for predicting the martial art gym. This is a little bit counterintuitive, but it still makes a lot of sense, because in the martial art gym, you want to wear shoes. So this neural network just pick up this bare feet as the evidence for this prediction. So in the training set of the martial art gym, we may have a lot of images with people wearing no shoes, right? So how does this method work? So here I just give you a very brief introduction. So right now we want to build a connection between the internal feature map with a final output. So there is between the final convolution layer and the final output, there is a layer called global average pooling layer. So basically, this global average pooling is just trying to do some dimensionality reduction. That they will just average pool this unit activation map into a scalar value. Then after that, there will be a logistic regression to predict the categories. Because of this linear relations, we can actually switch the orders of the inner summation and our outer summation. So we can first have this feature map from each convolution filters, F1, F2 to Fn. Then we can multiply the knowledge weight in the logistic regression that associated with some categories. Then we have this W1 multiply the feature map 1, W2 multiply feature map 2. Then we can weight to sum all the feature map use the category weights. Then we can have this class activation map. So this class activation map is actually a spatial visualization of the activation. So if we average the feature map horizontally and vertically, we can actually end up with this predicted scores, which means this class activation map can visualize which region most relevant to the final prediction. So this class activation map can help us identify the most saliency and important regions relevant to the final prediction. So the method, since its development, and it has been widely used in many applications, such as here is a result that people use to identify the important region for video prediction. So the top left corner is this top one prediction from some video classification network. So given each one, we can generate a heat map to highlight the important regions. So you can see the attention of the neural network actually shifting around inside the video that try to capture the important region relevant to the prediction. So this method also have been used in many other domains, such as in medical imaging. So have been used by medical expert or AI researcher to interpret the mammogram classification as well as a chest X-ray classification. After this, also many follow-up works such as GradCam to further generalize this method to many other neural network models. So this is the first study that we just have a very small tweak on the neural network. Then we can make this AI model more explainable for classification. So for this internal activation, so you may wonder what the internal activation are doing. So we have some other work that try to quantify the interpretabilities of the individual units. So along with my colleague David Bao and Antonio Torraba, so we develop another method called network dissection that try to visualize the internal unit. Basically, we just compare the unit activation with predicted attributes and see their correlations. Then we can identify inside the neural network that there are actually many emergent concept detectors. Here I show 3 units that try to detect trademark, lamp, and face respectively. So we can identify all kinds of emergent detector inside the inner layers. We also can figure out the key units relevant to the final classification. So for example, here I show you 3 units relevant to the living room classification. So they are actually meaningful, you know. Top one will be the sofa detector, the second will be coffee table, and the third one is a fireplace. So all those concept detections is quite relevant to the classification of living room. So here are another top 3 units relevant to the classification of restaurants. So they are the tables, chairs, and food detectors. So you can see this neural network trained for scene classification. The internal representations actually know a lot of this meaningful concepts in order to classifying the scenes. So really doing some interpretable and meaningful decision making inside the model. So what we need to do is just go there and identify those interpretable concepts. Let's move into the second part. So this second case study is about how can we build a more steerable AI for image generation. You know, nowadays we have a lot of this amazing image generation model, largely from this generative adversarial network. So after we train this network through this adversarial training, then we can have a representation like this. Then when we input some random vector, then this model will synthesize realistic images. So over the years, we see amazing progress made by this image generation model, the GAN model. From 2014, the first publication of the GAN papers, and over the years, the image quality and the diversity are greatly improved, such as Big GAN and Style GAN V2 can synthesize the object in different shape and pose. Also, we have this amazing model from OpenAI. So it's an image translation model, can translate any written sentence into some image. So we have the armchair in the shape of avocado and a snail made of hop. So it's quite amazing because before this work, if you just Google avocado chair, you can get nothing from Google, which means this generative model, after we train on different concepts, it learned to be creative, learn how to compose some previous concept into some new concepts, then generate the image about that. So this is a basic model of this image generation. It's just like this, you know, after training, so we can throw a random vector as inputs, then this model will give us outputs. So nothing fancy. So we change the random vector as inputs, so the output will change. So here another random vector inputs, another output. So this image generation pipeline, so it's very easy to use. However, it still have a lot of issues. The most important issue is that it's very difficult to customize the outputs. For example, sometimes we may want outputs with different lighting condition. We may want output scene with different viewpoints. So current pipeline doesn't support this customization of the outputs. So this property is relevant to the steerability of deep generative model. So how can we better steer this model to customize the output? So we want to improve the steerability of the generative model beyond this amazing image generation capabilities. So along with my student, Yang and Shen, so we develop a very simple pipeline to identify the causality in the latent space. Basically, based on this image generation pipeline, we can apply some of the self predictors and extract some attributes. Then we can go back into the latent space and try to identify the cause effects relations between the latent space and the attribute space. So this pipeline is actually pretty simple. So starting from the latent space, we can sample a lot of random vectors, so each denoted by the blue dots. Then we can throw into the generator G. Then we can have the synthetic image space. Then we can apply a lot of the off-the-shelf predictors. Computer vision and the computer graphics researchers build a lot of these predictors that can extract labels from the image. So we just get some off-the-shelf predictors. So here we have a particular predictor that can predict indoor lighting condition of the scenes. Then we can have the attribute space to indicate indoor lighting intensity of the image. So here we can treat the predicted label as a pseudo label for these random vectors and train linear classifiers in the latent space that try to distinguish whether this image has indoor lighting or nature lighting. So it turns out inside the latent space, this linear classifier can achieve more than 90% accuracy. So we have the final, the important step called counterfactual verification. So the previous three steps just calculates the correlation between the attribute and the activation. So correlation doesn't indicate causality, right? So we want to escalate the correlation into causality. Then we have this counterfactual verification. So what we are doing is that we just verify, or we just vary the latent code through this learned boundary and observe how much attributes intensity change based on this intervention. So that can help us identify how reliable as well as a causal effect relations between the latent space and attribute space, right? So after we do this process, we can identify a lot of this reliable boundaries. So here, after we have this reliable boundaries, then what we can do is just push this latent codes into this subspace represented by the boundaries. So what we're doing is just add this long vector of this boundary. So here we have two images donated by Z1 and Z2. So synthesize the image in the middle. Then we can push latent codes gradually across the boundary. And then you can see the indoor lighting condition is greatly changed. The lamp is just turned on, and also the global lighting condition is changed. So here is a demo video showing that we can steer this generative model to turn on the light. So it's a very realistic manipulation. Not only about just the indoor lighting condition, we also can identify many other attributes in the latent space. So here's another very interesting result that we can also steer the generative model to change the scene view. So here is a view change result. This result is interesting because when we first train this model, the training data we have just the individual samples that download from the web. So we don't have this correspondent images with camera parameters, right? So all the images are individual and independent samples. Somehow, in order to synthesize the scenes, this generative model just identifies those meaningful directions to describe the whole scenes. So one of them is the scene views. We can go back into the latent space, identify them, then we can change, control the scene view of the output image. But you can see there are some artifacts there, so we still have a long way to go to improve the quality of the result. So here we can see that giving this straightforward image generation pipeline, we can close the loop, then go back into the latent space and manipulate the latent space. Then we can control and steer this generation to customize the outputs. So you may wonder, what are the individual units doing? In our previous work that we identified this representation node for classification actually have a lot of this emergent concept detectors. So what are those units doing in this generator network? So we also have some measure to identify the role of the individual units in the generative model. So we found out actually those individual units many of them emerge as a synthesizer for different concepts, such as they correspond to synthesized trees, sky, dome. So we have a lot of different concept synthesizers, and also we found out the distribution of those concepts actually change over the layers from this layer close to the random vector to the layers to the outputs. So based on this identified units, we can build some interactive image editing phase. So user can simply brush the regions. We can just turn on and turn off the activation of that unit. Then we can control the contents at those regions. So this kind of interactive content creation is a very promising direction that human can interact with the AI generators to create and change and edit the content. The previous work, are all that I try to identify the steerable concept in generator in a supervised way. But as the generative model become more and more popular, people start training this model on all sorts of images. So here we have a generative model. People train for cats generation, and here we have another generative model. People train for cartoon generation. So for those kind of images, so it's really difficult to annotate. It's maybe very expensive to annotate all those attributes relevant to the cat and this cartoon characters. Therefore, we want to develop some unsupervised learning method to identify the steerable dimensions. So we have this recent CVPR work that developed a method for unsupervised discovery of steerable dimensions. So what we are doing is that we look into the connection between the latent codes and the convolution activations. So we found out they are doing some linear transformation in the intermediate activation, and this feature difference is actually independent of the latent codes after this editing. Then we develop an unsupervised learning objective that try to maximize the variation of the feature difference. So by solving this objective, then we can identify a lot of steerable dimensions in an unsupervised way. So here I ignore the technical detail and just show you the demo that after we identify the steerable dimensions, and then we can have this interface. So the banners on the left are the identified dimensions. The user simply can just draw the bars and control the different concepts. So you can see after the learning, the steerable dimensions are aligned with different concepts inside the image, such as the pose or the texture of fur of the cat. So we can change all kinds of attributes relevant to things. Like for this one, we have this cartoon character generators. We can identify a lot of this different dimensions, such as the pose and the side of the mouth. So this kind of human-in-loop AI content creation will be a very important direction in the future, I think, because you can imagine how if we can let human work with this AI model to create new content, that will greatly reduce the barrier of content creation. Basically, everyone could be a creator and enjoy this creative process. It also can greatly reduce barriers, such as we may don't need this years of training to become a designer. We can just work with this AI model to create new content. So this is one of the future direction I'm pretty excited about, is human AI, human in the loop content creation. Then let's move into the third part, that how can we build more generalizable AI for this machine autonomy. As the deep learning model become more and more accurate, then people start using the models in this machine autonomy application, such as the self-driving. We can input the observations to the models, then the model can do this end-to-end control, then outputs the how to steer the wheel, whether we should accelerate brake. Of course, we cannot directly train and evaluate such AI model for autonomy in the real world, right? So what people doing is that we first prototype the whole training pipeline in the simulation engines. So in this simulation trainings, so one of the most popular training method is this reinforcement learning. We have an environment, and we also have this agent parameterized by this neural network. So it will receive the observation and the rewards from the environment and output the action to the environment. So this agent can learn from trial and error how to drive the car. However, we found out when we train this agent on this simulation environment, the training agent actually have a lot of problems. So this training agent is pretty generalizable to a lot of scenarios. So here is in testing time, this training agent just doing all kinds of crazy and running into this traffic cone and scratch the other cars. So the generalization of the agents is a big problem. To further address these issues, we have recent papers published at the QuAL that try to put experts in the loop. So we develop experts or human in the loop reinforcement learning pipelines. So for this interaction between agent and environment, we can actually put experts inside this loop to ensure the safety of the exploration. That also can make this agent behave more like a man. So for this dangerous situation, so the agent will actually intervene this process and take control of the car and demonstrate how to avoid the issues. So here I just ignore all the technical detail. So after this, we can actually have a human in the loop as a supervisor to instruct how to drive in the car. So here, my students try to teach the agents how to drive the cars. So you can see they just co-pilot with the AI model. And when this AI model doing crazy things, then my student will take control of the vehicle and demonstrate what is the right action to take to avoid the situation. So here, this demo video showing you this training process in real time. So rather than previous trial and error trainings, so we can have this human in the loop and to supervise as well as give demonstration to the agent. So here is a speed up process. So after about 20 minutes training, so you can see this agent already know reasonably well how to drive the car inside the environment. Right now there is no control here. This agent just drive in autonomous mode. So this kind of human in loop reinforcement learning will also be a very important directions. Previously the safety of exploration and IO algorithm is an issue. Then how can we better put human in the loop to interact with agents will be a very important future direction. Besides, to improve the sample efficiency through human, we also have some methods that try to improve the diversity of the environment. For this environment, previous reinforcement learning environments are all fixed. But we want to improve the diversity of the environment. So we build some elementary traffic blocks. Then we develop some algorithm. It's some procedure generation algorithm that can sample from the predefined environment, then put them together, then generate new environments, new driving road based on this algorithm. So we can basically have a unlimited number of environments. Then each environment can be a new or interactive environment for the agent. So here I show you some generated maps from our algorithm. So we can also evaluate the generalization ability of the agent. So we can split those data into training and testing. So we found out the generalizability of the agent is greatly improved as we have a higher environment diversity. So this plot showing you the experimental results. On the horizontal axis is the number of training maps. The vertical axis is the performance on the training set as well as on the test set. So we have 50 holdout maps. So you can see as we have more training maps, the generalization ability of the agent is improved. Like after we have 100 training maps, then the performers, testing and training performers matched. So here is some demo video to show this generalizable agents. So this agent, you can see, is very robust to a lot of obstacles and the driving situations. You know, this agent even can know how to wait in front of the queue, and they can finish the navigation task. Finally, you can see this agent even can identify some shortcut, like how to just bypass 2 traffic cone and reach the destination as soon as possible. So this simulator is already open sourced. So it's called MetaDrive. So we release also technical reports and some benchmark based on this MetaDrive. So feel free to try this driving simulators and join our team to develop the simulator. So here is a summary. So in this tutorial, so I give you a very short introduction on 3 case studies. How can we build explainable AI for image classification? Also, how can we build more steerable AI for generation? And how can we build generalizable AI for autonomy? So eventually, we want to move towards human-centric AI. You know, the human-centric AI relevant to many properties of the AI models. You know, in this field, not all people only care about the performance. So here I would like to argue that the performance of the AI model is just one dimension. There are many other dimensions and properties we should also care about. So previously I already showed you that explainability, steerability, and generalizability are very important properties of the AI models. So many other properties such as modularity, fairness, or robustness. Those properties are very crucial to our human beings if we really want to deploy the AI models in the real world. So we should improve the all-around abilities of the AI models beyond just the performance, right? So based on this human-centric AI, there are many impact areas I'm pretty excited about. For example, for this content creation, how can we have human interact with this generation process to customize the output? Also in healthcare, we don't want to replace our human doctor, so we want the medical AI can work with our medical experts to join to make more informative decisions for our patients. Or also in this physical applications such as self-driving and the collaborative robots. So we want human can better understand the decision-making process of the AI models. We also want to want the AI models or machines can understand the intention and belief of our human beings, so they can have a mutual understanding. Also, there are a lot of societal impact and policies relevant to this human-centric AI we should further explore. And we also want to build more interpretable models for all the applications. So that's it. So this is the end of my talk. So I hope these case studies can give you better ideas. Also, this concrete examples, how can we approach this human-centric AI? So all the papers and the code are available at my webpage. So I'm very happy to chat with you later. Bye-bye.